I do have a question on anything. So we don't have a lecture on Friday, and Friday morning office hour is also canceled. So I'll make sure that I'll get everything covered for homework 7, tutorial 7, so we'll be good on that. I think tutorial 7 is due Friday, right? Due Friday midnight, and homework 7 is due, it was due Monday, because during the fall break, so we changed it to Wednesday. I'll do the best to cover every single problem that you may have a question on today. If not, I will pre-record it as a lecture and post it to the Friday's lecture, Friday's slot on my website. Can't wait for the full break, right? It's too stressful. Want to break? Yeah, me too. But I need to work. I have to travel to a conference and give a talk there. All right, let's get started. Any other questions? Anything? No? But the good part is I'm traveling home and I can see my dog. I miss my dog so much. It's a good part of it. So remember last time we talked about the capacitors in series and parallel. It's a big portion of the homework. You'll see a lot of problems ask you to calculate the overall equivalent capacitance or the inductors. So remember that for capacitor, the way we modeled it is the current flowing inside, flowing into it, and I equals what? C dV dt, right? But why? Do you remember C times V equals Q, right? Q over T is current. That's by definition. So the amount of charges flowing through a unit cross section of the conductor within a unit time frame, and that's current. That's the definition of current. It's just the amount of charges flowing through a cross section of the metal conductor. So charges divided by Q divided by T is giving you I. So that's the definition of current, right? Okay, so C times V is Q. You will learn that in physics. So Q is always on the top. Okay, Q divided by C is V, right? CV is Q. This is difficult to remember. It also happens to me as well. So the way I remember it is Q is always on the top. Q is the queen, and C is the Charlie and Victor. So they are the two assists to the queen. So they are at the bottom here. So the queen is on the top. So you always Q on the top and then C and V. That's how you remember that. CV is Q. So Q over T is I. Make sense? Right? So that's why it's a C dV dt. C dV dt. Remember that, please. So you have a series capacitor, C1, C2, and I covered this on Monday. I told you that a sine wave is able to pass capacitor. It's a short circuit. It's like a wire for alternating signal. Why? It's because it's repelling it, right? Even though there's no physical connection. But whenever you have a voltage here, it's equivalent, for example, it's sending charges to one of the plates. And because the charges are accumulating here, it's repelling the same amount of positive charges away from the other plate. Or you can say it's attracting negative charges to it. It's the same thing, okay? It's repelling it away. So that's why when you have this kind of pattern being injected into the plate, it's also repelling the same pattern there. So you are seeing the same signal exactly on the two sides of the cap. That's why we treat it as a short circuit for alternating voltages or signals. Make sense? But if you have a static voltage, 5 volts, do you have a voltage across it? Yes. There's the voltage. Is there current? If it's not alternating, there's no current. Static electric field, no current. If you change it, yes, there will be current. But if you don't change static charges, it's just a disconnect circuit for DC voltage. It's always DC. Voltage is not changing, it's accumulating over there. There will be an energy stored in the cap, however, there's no current. So whenever it's asking you to calculate the energy, so you'll see this problem a lot in homework. Energy stored in the cap. You are trying to use, integrate power. So how to get power? IT times VT. Where's I? Static, no I. So the equation, I don't know how to derive it, but the equation as a conclusion being provided to this class is if it's asking you to calculate the energy stored in the cap, so energy, use the this symbol, and that equals half CV squared. That's how you calculate it if you see a problem asking you to calculate the energy stored in the cap. It's going to be half and C times V, right? Times V squared, sorry. You're not using current times voltage to get the power and then integrate it to get the energy. No. It's asking for a static energy stored, like stored in the battery. Whatever energy is stored in the battery. So caps are, if you make the caps huge, they can behave like a battery actually. Yeah, they're batteries. So the energy stored in the cap is basically this. Okay, keep that in mind. It's a lot, happens a lot in the homework. So for this one, we know it's going to pass this sine wave like a short circuit. So these two caps are in series. And let's say this is I, whatever I is alternating I, it's a current. It's going to go through this wire. They're in series. If you're not here on Monday, you are still confusing, like why a voltage or current can go through it. So just keep that in mind. If you have an alternating voltage or current, it's going to go through it. It's a short circuit for alternating signals. Okay, just keep that in mind. So I equals what? So you have so we're trying to calculate the equivalent capacitance. Right? So overall I equals C equivalent dV dt, right? Okay, so d, let's just write down dV dt. That's plus minus V. No problem by far. Okay? And since V is the two voltages added together, so we got a V1, V2. So eventually this equals C equivalent dV1 plus V2 over dt. And that equals C equivalent dV1 dt plus dV2 dt. And because we know it's the same current going through, it's the same current, it's a short circuit. So I also equals C1 dV1 dt and C2 dV2 dt, right? So this becomes C equivalent d1 over dt, which is basically I over C1. Okay? So you can get I cancelled. It becomes 1. So this gives you C equivalent equals 1 over C1 plus 1 over C2. That's a conclusion we need to know, because almost like 60% of the problems asking to use this conclusion. It looks like a parallel resistor, but it's in series. So the capacitors in series performs very similar to the. I don't want to say it's performed similar, because these are totally different stuff, right? But I mean the conclusion to calculate the equivalent resistance or the equivalent capacitor, it uses the same equation. Keep that in mind. So I'll just directly write down other conclusions for this. Okay, C1, C2, if you connect it that way, you can imagine they are actually physically connected like that. So eventually it's just forming a big cap, a very big cap. It's a C1 plus C2, right? Okay? For inductors, if you place two inductors in series, L1, L2, the total inductance, equivalent inductance, will be L1 plus L2. That makes sense because they're in series. So these are just coils, right? In series, you add them together. Okay, if you have inductors in parallel, L1, L2. So L equivalent equals L1 in parallel with L2. So it's 1 over L1 plus 1 over L2. Okay.
Is there a reason the variable is L?
Good question, actually.
Was it just that's what they're writing?
Yeah, inductance.
Is it like the unit?
No, units Henry. I don't know. You can search for that, right? Real quick and see how that works. So inductors, L's. Okay, you have to use this a lot. Let's take one example from the tutorial first, since due Friday.
Because apparently it was Henry Lenz, so L's for his last name.
Last name? Good to know. Thanks. Alright, so most of you were not here. So let's look at this first. I just talked about the capacitors. When you have a static voltage, after a long time, the voltage is not changing, there's no current. So the problem we looked at was this one. Yeah, we'll just skim through this really quick since a lot of you were not here on Monday. So 10 volts, okay, 10 volts. It's just a resistor connected to the capacitor, another resistor. So what's happening is, if after a long time you treat this guy as a disconnect circuit, so it's just basically a voltage source with a resistor, another resistor, and disconnected, another resistor. All right, so it's asking you what's the current in here after a long time you turn it on. What's the current? No current. It's disconnected. DC, right? DC is not always alternating like a sine wave. It's not. It's DC, so there's no current. If it's a sine wave, there's a current. There's no current. So I has to be 0. What is V? The V is the same V here. So the V here is the same V here. They are equal. Because there's no voltage, no current, no voltage drop. So V here is the same as the V here at the tip. If this is grounded, usually we ground it, right? That's how to solve a problem like this. And so you'll see the signals. The signals being given is like a ramp. All right. So that's V, right? That's V. Because we know the equation is I C dV dt. So the V changing upon time. So that's why the slope here times C will be I. Here's the V, the source, doing the ramp voltage. And we just use delta Y divided by delta, since it's linear, so delta Y divided by delta X is a constant. Okay, so that's why the current times the constant is still a constant. So the current during this period will be whatever, you just use this equation, and eventually you are getting a constant here for I. Okay? Same principle applied to this one. Slope is 0, so no I. Makes sense, right? So what does that mean? What slope is 0 for voltage? It's a DC voltage. DC voltage, not AC. AC is alternate current. DC is direct current, right? So DC is a constant voltage. So a constant voltage is not providing any current into it because it's a static charge. A static charge is being accumulated at the two plates. And then you got a negative slope. Negative slope, that's why it becomes negative current. So it's a current flowing to the bottom plate. Okay, so that's why it's a negative current. And another problem you'll see here, so it's not using a voltage anymore, it's using a current, directly dumping current into it, which is fine because if you know that I equals C dV dt, so you'll know V equals, just calculate reverse in the backwards, just giving you 1 over C and integrate from 0 to T for I, right? It's basically the same stuff. Okay? So if you're directly dumping current to the cap, you could do it, right? Since I told you on Monday, you should always treat the capacitor as a bucket, water bucket. You are filling the bucket with water using a hose, right? You are filling it up. So this is basically a hose, filling water into the bucket. Okay? So it has an initial voltage, which is 1 volt being stored in the cap. The capacitor is able to store charges. So it's initially stored 1 volt across the 2 plates, and then you start dumping current into it. So it's going to follow this equation for the voltages accumulated after that, beyond that initial voltage. So eventually you are adding this one to V0. At the very beginning you have a voltage stored in there, and then you start dumping more. So this is how much you dumped into the bucket. Then you add it to the original voltage, so you can get a VT. This is actually VT, right? Make sense? Any questions on this? Okay. Like I said, after a while, you initial energy stored in there. So it's already told you that. Oh, I can show this actually. So 10 volts initial at T0. 10 volts, so V0 equals 10 volts. So I got 10 volts stored in the cap at the T0. Okay, so voltage is already given, and this is the equation to calculate for energy stored in the cap. What's the parameter do you need to know to calculate the energy stored in there? What is missing? Oh, so these are constants, right? This is the only parameter you need to know. How much voltage you stored in the cap. And it's already told you it's 10 volts. So you can easily calculate the energy stored in there. So for part E, it's super simple, just one equation, one step. Make sense? Okay. Inductors. I got a little inductor here. It looks very similar to resistors, but I can tell it's different in the symbol. Okay. So it works similarly, but the thing is, inductor is a coil. If you have alternating current flow through it, it's going to generate a magnetic field and the voltage across it. It's really interesting. So it's like an alternating current flows through it. It's going to generate a voltage, and that voltage is dominated by this, determined by this equation, L di dt. All right. There are just 2 equations. So for all the nonlinear circuits we are going to cover in the homework tutorial 7, it's basically just 2 equations, right? One is used to model capacitors, which is the C dV dt stuff. Another one is L di dt, that's it. So if you flow a current through it, alternating current, you are getting a voltage across it. Okay? How that works. The God makes it magical. Follow the God, follow your heart, right? It's gonna work. Physics, right? Why the earth exists? This is something exists on the earth. Magical, right? You got current flow through it, it generates a magnetic field. Okay? And it has to be alternating current. Why? If you look at the equation. If it's not alternating, right? It's not changing over T. What is the di dt? 0. What's the voltage? 0 voltage across the inductor. What does that mean? It's disconnected. 0 voltage across something. 0 voltage across something. Does that mean that part is disconnected from the circuit or something else? Shorted, yes. No drop. It's a wire. So if there's no alternating current, it performs like a wire. After you have a DC constant current flows through it for a while, you turn it on for a while, it performs like a wire. It's a short circuit. Okay? So this question is asking you to calculate the current flows through this guy. Oh, there's a voltage across it. Okay? After turning it on for a while, whenever it's settled, not changing anymore, it's a DC, right? It's DC. How to calculate the current through it? I know it's asking for voltage, but also asking for current as well. So how to calculate the current? It's a current divider, right? You have two resistors. This is ignored. It's a wire. Two resistors and one main current. You can definitely calculate for the current in here. All right. Current calculated. What's the voltage though? All right, I told you it's a wire. 0. Okay. It's asking you if it's providing a ramp. So you can imagine it must be current, right? Because the dt. It's the alternating current this time. What's the equation to model a capacitor though? Which equals what?
C equals Q.
Yeah, C equals Q?
CV.
Oh, CV equals Q, yes. What else? We are modeling the capacitor by getting the current or voltage.
Q equals C.
Yeah, see? It takes some time to remember all these models. So we model it as I across it, right? So I equals what? C dV dt. For inductor, we model the V across it, and V equals what? L di dt. I'll just have to repeat it 100 times this semester so you can remember it. Okay. But luckily we only have 2, not too much. Not like physics, you have 100 different times the equations you need to memorize, right? It's better, I think. Electrical engineering is better. Easier, I can tell. Couldn't do physics. So current is alternating, it's a linear current. Because the di dt, so are doing the slope over here, right? It's di dt, it's a slope. It's a linear current, so you can definitely know the slope is a constant. What is it? 2 amps on the y and 2 seconds on the axis. So it's 2 divided by 2 is 1, right? Is 1. And you times the inductance, which is 100 millihenry. 100 millihenry. So eventually 1 times 100 millihenry is what? So the unit is volts, right? So 1 times 100 milli is 100 milli, right? So we're basically getting what? 100 millivolts. DC or alternating for this time frame before 2 seconds. It's gonna be constant a constant 1 millivolt DC voltage, right? Slope is 1 times 100 milli. You're getting 100 millivolts DC. So if I'm asking you to draw the diagram for the voltage, you'll know that from 0 to 2 seconds, I'm getting 100 millivolts, right? Then do this from 2 to what? To 5. From 2 to 5, what's the slope here? 1, 2, 3, 4, 5. 5 divided by 3, right? It's also a DC voltage, but negative. 5 over 3, right? And then here is 1, 2 divided by 1, 2, 3, 4, 5. So it's 0.4. What? It's positive, right? So this is 0.4 milli. So it's DC, 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 right? DC. So it has to be this guy, right? It's a multiple choice problem. Shows you 3 diagrams. It has to be this guy. Right. Any questions by far? Another thing can confuse you a little bit, which is inductor can store a initial current inside as well. It's like the voltage, the previous problem we just ran through. So the voltage can store initial voltage here like 10 millivolts, and then you start dumping it. So eventually the voltage equals 10 millivolts plus whatever being dumped into it. Okay, that's how I calculate the voltage across this guy. So same for the inductors, it is able to store initial current into it as well. So stores the initial current inside. So the final current equals stores the initial current. Stores the initial voltage, I'm sorry. Stores the initial voltage across. Wait, that's so here. Let's just read the problem and see what's really happening here. Because here, V T equals L dit dt, right? So it of it equals 1 over L. Right? So it is able to store initial current. So eventually the final current equals this plus the initial current in there. Just same concept. If you start dumping a current into it, here's a voltage source. So usually they model it as a voltage source. Voltage source on there. VT. Depending on what is given to you, right? Let me see if there's another one that if I tell you that there's an initial current stores in the inductor, so at t equals 0, what's the energy stored in the inductor? I0 times 0, yeah. So the energy is a half L times I0 square. Okay, that's how calculate energy. For a problem like this, and this class is has a really fast pace, I think. Homework due week after week, right? Yeah. So when I teach at Forest College, I don't do that this way. So it's more engaging. We have circuit simulation tools. So in homework assignments, students build a circuit. There are not too many problems. Usually just 5, no more than 5. So as long as they know how to do this problem, and then they do a simulation and verify their answers with the simulations. And I was able to give quizzes in the class, so I can keep all the students engaged. They have to come. I'm not counting attendance, right? So if you give quizzes, they will come. And they get nervous. I like to see they're getting just kidding. So when they're getting nervous, they get engaged. Actually, eventually they appreciate it since they learned. You see, like we have more than 50% of students are not coming every time. You know, if I have quizzes, they will come. They come, they learn, they get engaged, they have fun. They will give me a high rating after at the end of the semester. But now I just couldn't do anything. No simulations. The rating will be low, and you guys are getting overwhelmed. But eventually, you are learning exactly the same thing. No difference. Eventually, the skill set of the students over there is probably even more because they know how to do simulations. They have more time to working on other stuff. I think it's just better. Here I have to do this, you know. If I don't cover the problems, you won't get a grade, right? You won't get the credits every week. Okay. I cannot add anything else but cover the homework problems every time. So look at this one. Inductors, just treat them as resistors, right? It's not that difficult. Just asking you to find out the equivalent inductors, equivalent inductance of the two terminals over here, all right? So what's happening? Looks complicated, actually it's not. Super simple. If you see this problem in the homework, you should be happy. You should be happy to see it because it's very simple. What's happening is you got the two nodes, you just assume there's a current flowing into it, right? At the end here, you got this getting split into two branches. You got two here, they are basically in series. I'll just write it down for you. So you couldn't see the label, but I'll tell you this is L6 and this is L8. So for these two inductors, you're getting L6 plus L8, right? And that two inductors is in parallel with L5. And so you, as these two nodes, you have this. All right? And then you keep looking back, you see that L2 is in series with the whole thing here. L2 added to this network. And eventually this whole thing is in parallel with L4. All right? And then the whole thing here is in series with L7. And eventually, this entire network is in parallel with L3. Why do we have to do this? All right. So now you got the overall inductance across these two terminals, and that is in series with L1. So eventually, do this. What is this testing? Testing your patience, right? You have to be patient to become an engineer, so that makes sense. So when you have to put in here, it looks like it's okay to show this since you couldn't see the details anyway. So so these inductors are similar to resistors. If you have L1, for example, L1 in parallel with L2, what's the equivalent inductance of these two? It's just L1 times L2 over L1 plus L2, okay? For L1 in series with L2, just a simply L1 plus L2, okay? So you can plug this in here to figure things out. That's for inductors. I think you will see this problem probably like 4 times in tutorials and homework assignments, just inductors. And adding the capacitors version, you will probably see like somewhere around 6 to 8 similar stuff. But it's pretty simple though, mentally simple. But emotionally hard. How to deal with this? Did I tell you that series capacitors C1, C2, what's the equivalent capacitance? Remember, it's 1 over C1 plus 1 over C2, right? This is basically C1 times C2 over C1 plus C2. Yeah, make it simple. If you have parallel capacitors, C1, C2. So it's C1 plus C2, right? Okay, so for this guy, it's asking you that determine equivalent capacitance across terminals of A and C. So A and C, what you have across A and C. So it's getting split into 2 branches, but connected to A and C, there's one cap, so it becomes like C4 in parallel with everything here, right? Make sense? C4 in parallel with the whole thing. So what is the whole thing here? So on over here, you are getting C1, C1 and C3 in series, right? So this is C1, C3, C1 plus C3. Oh, in parallel with this, and then in parallel with everything here. These are 1, 2, 3 branches. So in here, we have C2 times here, and C2 plus this. C2 is in series with the whole thing here, right? Make sense? So that's why C2 times the whole thing here, and C2 plus the whole thing here as well. That's a series capacitance. And then we need to find out what's the capacitance over here. So these are in parallel. For capacitors in parallel, it's better because we just add them together. But within it, we have to figure that out. So it's going to be C5 times C7 over C5 plus C7, right? Plus these two series capacitors, C6 times C8, C6 plus C8, right? And copy it over here. I know I'm not going to get good comments in teaching evaluation anyway, so by looking at your poker face, I know you're getting bored. Yeah. Just do whatever you have to do. Another thing you need to know, we still have like 13 minutes. Self-inductance and mutual inductance. So I'll draw this problem for you guys. So if I got 3 inductors in series or in parallel, doesn't matter. So they will they will interfere with each other if they are physically placed close enough to each other. And they labeled it this way to indicate that if they are wound in the same direction, because usually how that works is you wind a coil here, right? You wind a coil. I think I have a better example on my website. I know it's gonna be confusing, so that's why I posted a PDF there. This one. Let's go coupled inductors. So you only consider mutual inductance when it tells you to do so. Okay. A lot of times, for example, the inductor network, it didn't ask you to calculate the mutual inductance, so you don't have to do it. But some of the problems they're asking you to add it or minus that mutual inductance to it, so you have to consider that mutual inductance. So what happens is, if you place the two inductors close enough to each other, because if you run currents through it, it's gonna generate a magnetic field around it. So that alternating magnetic field will cut through. It's not physically cutting it, but the field is going to cut through the metal. So whenever you have an alternating magnetic field cutting through the metal, it's going to create a current through it. Right? What's that called? Faraday law? Whatever. That's a fundamental principle of the power plant. That's how they generate currents, right? So they let the metal cut through the magnetic field, so it's going to generate induced current in the metal. So we got power, right? So it's the same thing. If you have an inductor close enough to another one, so they both are generating magnetic field, and that magnetic field will cut through the other inductor's metal and will creating a current in addition to whatever current already in there. So it's called it's being generated by the mutual inductance, depending on how close you place them together, right? If you place one in US, one in China, definitely they won't interfere with each other. But if you place them close enough, they will. And it's also depending on. So if you just look at the schematic, could you tell if they are physically placed next to each other or not? It's just showing an electrical connection. It's not showing the physical connection. Does that make sense? In schematic, you can draw a wire, but doesn't mean that they are placed close enough to generate a certain mutual inductance in between each other. So schematic's not showing physical placement. I'll show one quick example. I think most of you got that, but let me show you this. So for example, you are designing a PCB board. It's a printed circuit board. And you have two design files, and one is called schematic, right? Like a schematic, like, I'll just show you one of them, like this, okay? So place a schematic in a certain frame in the design file, and you'll show that you label them the same name, so they are physically connected. However, it doesn't matter where you place this symbol because it doesn't show the physical placement. You can put it here, you can put it somewhere else. It doesn't matter. So eventually, you got to the layout of the circuit board. You can arrange all the locations of the parts. If you need them to be at the edge, for example, the pin headers, they need to be the edge, so it's easier for the users to connect wires to it. Okay. Or other components, you want to place it next to the pin header for some reason, you can do it. But in the schematic, you can place them anywhere you want. Anywhere makes more sense, just do it. So the same concept applies to this sort of problem. You know, if they draw these two, doesn't mean that they are close enough to have a significant mutual inductance. But only when they tell you that there is a significant mutual inductance, then you have to consider that. And the way to calculate that is very simple, actually. So for example, there's a current going, another thing I didn't cover really quick. Let's go back to this diagram. So you have to be aware of this cumulative coupled inductors and the differentially coupled inductors are performing in a different way. So it's all depending on if you are running the same direction of currents in the coupled inductors. So for the first example, they are wound in the same, the coil are wound in the same direction. So eventually it runs the current. You see the current going through here, going to the back, and eventually follows here. It follows the same direction, okay? So they are cumulative coupled. So eventually you have the overall equivalent inductance of the two. It's L1 plus L2 plus the two mutual inductance. Because this is creating a mutual inductance here, and this is also creating a mutual inductance over here as well. So two, you got two being added to the overall inductance. So for the ones are differentially coupled. So the wires are wound in a different direction. So they are running current in the opposite direction. So in that case, actually it's deducting inductance from each one. So it's minus 2 is basically L1 minus 1 and L2 minus another one. Okay? So that's why it's L1 plus L2 minus 2 of the mutual inductance. So they're actually reducing the overall inductance overall. Okay? So in the homework assignments, it's going to indicate the direction that how you wind that coil here by a dot. If the dot are at the same direction, it shows that they are wound at the same direction. Otherwise, it's a different direction. Okay. Does that make sense? So these two are definitely differentially coupled, right? But these two are cumulatively coupled, and these two are differentially coupled. Make sense? But since it's running a current in the same direction, it's running a current in that direction. But the thing is, it's still creating a differentially coupled mutual inductance. It's because they are wound in the different direction. That's why I show the dot here. So let me just show you what the question looks like. So the first one, it asks you to calculate V1. This is I. So definitely the self-inductance, self-induced inductance, right? Just a self. It's L di, it's the same I dt, no problem. It's the same. It's a V1. It's self-induced inductance first, and then you are having interference here. It's a mutual inductance also appears, but the thing is, this guy is running the current in a different direction because it's getting wound in the different directions. That's why you have to minus that. This L1, L2, L3. Is M1, 2, same current, dt. That's the voltage generated by the mutual inductance applied to this inductor. And because this one has the same direction for the dot, so we do a plus 1 and 3, that's the mutual inductance between 1 and 3, and di dt. For V2, something you have to know, for V2, it equals L2 di dt and compare these two. They are having a negative mutual inductance. No, not negative. So negative voltage created by the differentially coupled inductors. So that M1, 2 di dt, and these two are differentially coupled as well. So you do M2, 3 di dt. So for V3 is L3 di dt. The mutual inductance from L1 is positive, and the mutual inductance from L2 is negative. So there must be a confusion here. Because they are wound in a different direction, so why the voltage of the V2 is the same as V1? See? We're keeping the self-induced one positive for both. Right? It's just a coil. It's just a coil. Doesn't matter you want it this way or the other way. So the direction of the coil is not going to determine the polarity of the voltage across it, but the mutual one determines it. The sign. It's just a coil. Just looking at self, the self-induced, right? You just grab a coil. Doesn't matter which direction you want it. It's gonna be the same voltage. If you define here, plus minus, it's gonna be the same voltage. But the mutual one will run a different way. Okay, keep that in mind. This can be confused. What else? Let's see. There's another one. So very quickly here. I know we don't have one more minute, but very quickly. Just hopefully we can do it on Friday. So for this problem, you'll see if the current I1 is a mesh problem. If I1 is flowing that way, if you are defining I3 and I2, right? If the overall current is I3 minus I2, so the current flowing into the dot, so the mutual inductance created here and contributed to this one will be positive, because if you use I3 minus I2, it's the current flowing into the dot. It's going to be the same as this one flowing into the dot. So just add the mutual inductance to it when we're calculating the voltage. So calculate the voltage here, right? You got a V equals L1, right? L1 di dt. So if you want to calculate the mutual inductance contribution to the voltage, and you are using I3 minus I2, it's going to be positive, because the current I3 minus I2 is also flowing into the dot. Okay? So I think I'm going to record a video lecture and post it to the website for homework 7. So this is everything about tutorial 7 already. Okay? We'll see you on Wednesday next week.
How will we calculate our mutual inductance?
It's given.
It would be given?
Yeah.
Okay. Alright, that makes much more easier.
Easier, yeah.
It's like,
Yeah, these problems are easy. These problems are easy. It's just like two equations.
okay. So we'll be given mutual inductance and our L's for all of our, I guess that's also inductance. Okay, cool. And then we're just